Hello, students. Have you ever wondered why sodium hydroxide is so useful in the lab? Or why ammonium hydroxide is a go-to reagent for identifying metal ions? These two hydroxides, commonly used in laboratories, have unique abilities to react with salt solutions in interesting ways. Let's dive into the fascinating reactions that happen when these hydroxides interact with salts, forming either insoluble precipitates or soluble complexes. Sodium hydroxide and ammonium hydroxide help us detect metal ions and explore the chemistry behind precipitation and complex formation. These reactions are crucial in qualitative analysis, not just in the lab but also in water treatment, where they help remove impurities. Now, let's take a closer look at the reactions of sodium hydroxide with calcium and magnesium salts. When calcium nitrate reacts with sodium hydroxide, calcium hydroxide is formed and it's a white precipitate. The equation goes like this: calcium nitrate, Ca nitrate 2, reacts with 2 moles of sodium hydroxide to NaOH to produce calcium hydroxide, Ca hydroxide 2, and 2 moles of sodium nitrate to Na nitrate. Calcium hydroxide is nearly insoluble in water, and that's why it forms a solid precipitate. It's like when you mix chalk in water, it doesn't dissolve fully and instead forms a cloudy solution. Similarly, magnesium chloride reacts with sodium hydroxide to form magnesium hydroxide, which also appears as a white precipitate. The reaction follows the equation: magnesium chloride, Mg chloride 2, reacts with 2 moles of sodium hydroxide to NaOH to produce magnesium hydroxide, Mg hydroxide 2, and 2 moles of sodium chloride to NaCl. Magnesium hydroxide, like calcium hydroxide, is practically insoluble in water and forms that familiar cloudy solution. These reactions are essential in understanding how hard water can be treated in everyday life. Let's move on to iron and copper salts. Sodium hydroxide reacts with iron, 2, salts like iron, 2, sulfate to form iron, 2, hydroxide, a dirty green precipitate. The equation for this reaction is iron, 2, sulfate, Fe sulfate 4, reacts with 2 moles of sodium hydroxide to NaOH to form iron, 2, hydroxide, Fe hydroxide 2, and sodium sulfate, Na2 sulfate. This iron hydroxide is a typical example of how iron, 2, forms when exposed to hydroxides, and it's insoluble in excess sodium hydroxide. Similarly, copper sulfate reacts with sodium hydroxide to form copper, 2, hydroxide, a pale blue precipitate. The reaction goes like this: copper sulfate, Cu sulfate 4, reacts with 2 moles of sodium hydroxide to NaOH to form copper, 2, hydroxide, Cu hydroxide 2, and sodium sulfate, Na2 sulfate. Notice how the pale blue color of copper, 2, hydroxide is an easy indicator in the lab for identifying copper ions. These reactions give us a visual clue for metal identification. Now, let's talk about zinc and lead salts. Zinc sulfate reacts with sodium hydroxide to form zinc hydroxide, a gelatinous white precipitate. The equation goes like this: zinc sulfate, Zn sulfate 4, reacts with 2 moles of sodium hydroxide to NaOH to form zinc hydroxide, Zn hydroxide 2, and sodium sulfate, Na2 sulfate. Zinc hydroxide is different from iron hydroxide because it's soluble in excess sodium hydroxide, forming a colorless solution of sodium zincate. This is an interesting example of how some hydroxides can dissolve in excess base. In the case of lead, 2, nitrate, when it reacts with sodium hydroxide, lead, 2, hydroxide, a chalky white precipitate, is formed. The equation is lead, 2, nitrate, Pb nitrate 2, reacts with 2 moles of sodium hydroxide to NaOH to form lead, 2, hydroxide, Pb hydroxide 2, and sodium nitrate NaNO3. Lead hydroxide is soluble in excess sodium hydroxide, forming a colorless solution of sodium plumbate. This property makes lead a prime candidate for analysis in the lab using sodium hydroxide. Moving on to ammonium hydroxide, we see it's a bit different from sodium hydroxide. While sodium hydroxide typically forms precipitates with metal salts, ammonium hydroxide can either form precipitates or dissolve in excess, creating complex salts. For example, when calcium nitrate reacts with ammonium hydroxide, no precipitate forms. The reaction is calcium nitrate, Ca nitrate 2, reacts with ammonium hydroxide, NH4O, and no precipitate is observed because calcium hydroxide is only sparingly soluble. Magnesium chloride reacts with ammonium hydroxide to form magnesium hydroxide, Mg hydroxide 2, just like sodium hydroxide. The equation is magnesium chloride, Mg chloride 2, reacts with ammonium hydroxide, NH4O, to produce magnesium hydroxide, Mg hydroxide 2, and ammonium chloride, NH4Cl. Magnesium hydroxide, again, is a white precipitate and insoluble in excess ammonium hydroxide. Let's take a deeper look at how ammonium hydroxide reacts with copper and zinc salts, where the reaction leads to complex salt formation. For copper, 2-sulfate, when ammonium hydroxide is added, copper hydroxide forms initially, but in excess, it dissolves, forming a deep blue solution of a copper-ammonia complex. The reaction is copper sulfate, Cu sulfate 4, reacts with ammonium hydroxide, NH4OH, to form copper hydroxide, Cu hydroxide 2, and ammonium sulfate, NH4 sulfate. With excess ammonium hydroxide, copper hydroxide dissolves and forms a complex salt, copper-ammonia complex, of 2. Similarly, zinc sulfate reacts with ammonium hydroxide to form zinc hydroxide, Zn hydroxide 2, which dissolves in excess ammonium hydroxide to form a colorless solution of zincate, SO4. This is a great example of how ammonium hydroxide can dissolve hydroxides of metals, forming soluble complexes, which makes it invaluable in analytical chemistry. To sum up, both sodium and ammonium hydroxide play crucial roles in reactions with metal salts. Sodium hydroxide is typically used to form precipitates of metal hydroxides, like calcium hydroxide or magnesium hydroxide. Ammonium hydroxide, on the other hand, not only forms precipitates but also dissolves in excess to form complex salts, which is useful in qualitative analysis. These reactions are not just academic, they have practical applications in water treatment, metal extraction, and industrial processes. I hope you now appreciate the chemistry behind these reactions, from the lab to real-world applications.